Yeah, that was
Yeah.
very good.
Here we go.
Is it on Spotify?
So it should be on Spotify. The sun is a mass of incandescent gas, a gigantic nuclear furnace where hydrogen is built into helium at a temperature of millions of degrees. That is actually on Spotify. It's a song by They Might Be Giants, which is kind of a band from the 90s. So if you want to check that out, it's called Why Does the Sun Shine is the name of the song. And the key element that I wanted to talk about for that song was the line about hydrogen being built into helium. Okay, so hydrogen is built Okay, and I think you guys have heard of that the sun builds hydrogen into helium. Can you guys tell me what that process is called? And I will call on somebody. Oh, Carlota speaking.
Oh, fusion?
It is called nuclear fusion. You might have heard of that. That's kind of what we're talking about. Nuclear fusion. And this is key here, that this word built is actually really good, because sometimes we say the sun burns hydrogen. Now that's actually not the case, because burning hydrogen is actually something that you have seen before. But that's not what the sun does. What happens when you burn hydrogen? Is iPad raising his hand or her hand? I don't know who iPad is.
Das bin ich, aber das war
It's
vorher.
Raffi, it's Raffi.
Ja, das
Okay,
ist,
okay,
ja, na.
okay. Rafa weiß nicht? Raffi weiß nicht? Okay, dann fragen wir mal.
Doesn't
Okay.
it like react with like the oxygen in
The
the air?
oxygen, exactly. You've seen this in chemistry class, okay?
Yeah. it
Your
was the
chemistry
first day.
teacher has done this test. You take a balloon and you fill it with hydrogen, and then you put a candle to it and it goes boom, yeah? And it's a pretty cool reaction, but that is not what happens when fusion occurs, okay? When hydrogen is burnt, okay, hydrogen burns. So I'll just write that up here, burning. It's kind of a side note. When you burn hydrogen, you take 2 hydrogen molecules and you combine it with 1 oxygen molecule and you get water out. And in chemistry, you probably have done that. So burning, you take 2 hydrogens and you combine it with an oxygen, out comes water. So burning hydrogen, the waste product is water, okay? Cool. Now, when we build hydrogen into helium, we do not burn it. The sun does not burn anything because there's no oxygen up there to facilitate that burning process. So instead, we're going to take hydrogen and we're going to build it into helium. So in order to do that, we have to talk for a second about hydrogen and helium in terms of their numbers that are attached here. We've introduced the concept that each nucleus comes with 2 numbers, 1 on the bottom and 1 on the top. So the bottom, yeah, question? No question.
What's
Okay.
that sound?
I don't know. I don't hear it. Okay. So there's a bottom number, and on the bottom, hydrogen here has what number? Just shout it out.
1.
2.
1. It is 1. The 2 goes with the helium. Nice job. So hydrogen has a 1 there, and helium has a 2. And what's the name of that number? And we have a correct.
That's the atomic number.
Atomic
Good.
number.
That's
Atomic.
fantastic. That is the wrong answer. I love that.
Atomic weight.
Charge number.
Good. So previously we
Atomic
talked
mass.
about this as atomic number. Whoopsie, scooch this down a little bit. But I told you that's like what chemistry teachers say at this point, but
The charge number.
it is the charge number, exactly. So
Aren't
we're
we
not
in
going to call this
chemistry?
atomic number. We're going to call this the charge. Okay, so the charge, and we don't put the plus in there, but of course, the nucleus of hydrogen, just a reminder what's in the nucleus of hydrogen. The nucleus of hydrogen, I like using that accent for some reason, gets me kind of happy. I'm not sure why. So we got our hydrogen. So we got the nucleus of hydrogen. That's just like a big fat positive thingamajigger, like that. Proton, that's the nucleus of hydrogen. So when we're just talking about the nucleus of hydrogen, that's just a proton. So then we also have a number up here, and that is a second number. What's the second number up here?
Atomic mass.
Atomic mass is the wrong answer. Love it. Very, very good. So
The nucleon number. It's the nucleon number.
good. So we do not call this atomic mass. And for a specific reason, this is for us the number of nucleons. Nucleon number. This down here was the charge number. That accent's a lot of fun now. Really enjoying that. Okay, charge number down here, nucleon number up there. Let's do the same thing for the helium over there on the right side. 2 down here. What's the number up there?
3.
2.
It could be 3 or 4 or 5, but the most common option is 4. So actually the top number, just a reminder about that, the top number is variable because many atoms have isotopes, and the isotopes vary in the number of the nucleons. Every helium has to have 2 protons, otherwise it's not helium, okay? Every hydrogen has to have 1 proton, otherwise it's not hydrogen. Every lithium needs to have 3, otherwise it's not lithium. Carbon 6, oxygen 8. You get the idea. That number is mandatory, otherwise this is not helium. The top number, however, can be different because we can vary the number of neutrons. So if you make a little picture of this thing, we got 1, 2, those are the neutrons, and then we have also our protons there. And let's go over here. So this is the positive charge, the protons, and these are the neutrons. Okay? Oh, that's pretty. I like that. I'm having a good time. It's all about me. All about me. I don't care if you're even here. Okay. Hey, you guys still here? Let's go. Okay, so we have that situation. Now, obviously, we have a problem here, right? Because we can't make one hydrogen nucleus simply into a helium nucleus. There's something missing here. So we need to have the building blocks to actually make this. And that's just a reminder, kind of like, whoop, there we go. That's kind of like helium, right? Whoop, there, yeah, all good. Yellow, green, whoop, that's fine.
Yeah.
Yeah, makes sense. So having one of these is not enough. How many of these should we use?
4.
2.
4 sounds like a good idea. Let's do that. So we're gonna make
6.
Oh, 6 is dumb. I like that. So we got 4 of these now, right? So here we go. So we got 4 of these. Good times. There's our 4 protons, and we get positive charges. Now, so it looks like we have a good situation where our nucleon number is now balanced. You guys agree? We have 4 nucleons on the left side, and we have 4 nucleons on the right side. Do you guys concur?
Mhm.
Yeah.
Yes.
You should concur because that's correct. So nucleon number needs to be conserved. That makes sense because you know, we have 4 blocks on the right side. We should have 4 blocks on the left side. We might be able to deal with the issue that some of the wrong color. However, that's still a problem, but we definitely need the right number of blocks. That's what we call nucleon conservation.
Isn't that like conservation of mass though too?
Yine. So nucleon conservation is true. How about conservation of mass? Is that true?
No.
No, that's what we talked about last time. So mass conservation is not true, but this is a true law for nuclear reactions. That's going to be helpful for us. But mass conservation is not true. And just a reminder about that, there's an equation that goes with that, right? And it's the famous equation that Einstein came up with. What's that equation?
E equals MC squared.
Good. So E equals, in that case, delta MC squared, meaning there's a
does delta mean?
change in the mass. If there's a change in the mass, there's energy released. And in our situation here, it is certainly true that, let's write it in blue, that energy is released in this process because guess what? The sun is hot and it shines, and that's why we are able to live on Earth, because the sun produces energy for us. Okay? Everything good so far?
Mm-hmm.
Uh-huh. No, not everything is good, because
Yes.
we still have a problem down here.
Yep.
The charges are not right. You see that? We
Yeah,
have
you're
four
right.
positives here, and we have 2 positives on the right. So the charges are not balanced. But guess what? Not only does nucleon conservation have to be true, it also has to be true that charge conservation holds. So not just this, we also need, oh, the Germans are going to hate me. So nucleon and charge conservation are true. So that means mass conservation not true, nucleon and charge number have to be conserved. 4 is not equal to 2. So we need to solve this problem.
What?
Well, they're not gonna hate you for something that they can't see. It's kind of hard.
What? Are you talking to me?
Yeah, it's kind of hard to see.
The board?
I can't. Does it say nucleon charge?
It says nucleon and charge conservation are true.
Oh. Okay. Thanks.
Okay, so that means if we look at the top here, this one right here is 4 times 1. And on the right, we have 4. And that is true. It holds. So this is our equation that we have here for our nucleons. And the nucleons are balanced. You guys okay with that?
Yes.
Okay.
Mm-hmm.
The charge conservation does not add up correctly. So if we look at the charge conservation down here, and I'll draw that in blue, right now, our situation is that we have 4 times 1 on the left side, and we have 2 on the right side, and that is obviously not true. You guys agree?
Yes.
So we need to have something additional on the left side. What could we add on the left side to make 4 into 2?
Could we add
Electron.
electrons?
We can add electrons, and specifically, let's talk about an electron. An electron, okay. Electron has what charge number?
0.
Negative.
-1.
Negative.
Oh.
Okay,
What was
the
that?
charge of an electron is -1. What is the nucleon number of an electron? How many nucleons are inside an electron?
0.
Zero.
Zero.
Of course.
It's
Because an
neutral.
electron is not a nucleon. Nucleons are protons and neutrons. That's it. So let's take a look.
Shut
We
the
now
fuck
have
Neutral.
added an electron. Are we set? Let's take a look. On the left side, we've got 4 minus 1. That's not enough. How many electrons do we need?
2.
2. If we have 2
Exactly.
electrons, we're going to be okay, and this equation will balance out. Now that we have 2 electrons combining with 4 hydrogen nuclei, that can react into a helium nucleus and release energy. Okay? The numbers work out now, but if we actually look at this situation, you should now be slightly unhappy with me, because this means something very strange. Remember, on the left side, we had 4 protons. on the right side, we have 2 protons and 2 neutrons. Now,
Wait,
let's number these. Like this could be proton 1. Okay? And let's say this is proton 1. That proton becomes that proton. All good. Make sense? Well, this proton becomes this proton. All good there. And now comes the wacky thing. We have this is proton 3, and we have an electron. And that third proton, together with the electron, must become a neutron. So protons can absorb an electron and turn into a neutron. And we have that happening twice here because this proton does the same thing. We also have an electron there, and it combines with a neutron to proton to make a neutron. So protons can turn into neutrons if they absorb an electron. So when we said over here that nucleon conservation is true, what we mean is the number of nucleons stays the same. But you can turn a red or green or whatever colors. We had here red and green, but you get, they can change colors. They can change colors, but the number of Lego blocks needs to stay the same.
I have a
Okay?
question.
Yes.
So I mean, theoretically, and if you want to be super basic, electrons don't have a mass, but they actually do. It's just like close to 0. But when you add it with a proton, which is 1, right? Then it is more. So is that where we get the
No. So
the gain
it's a
of mass?
really good question, but the masses are actually complicated. So the mass of a proton is not 1, it's about 1 nucleon mass or atomic mass unit, but it's not exactly that. We're going to get into the nitty gritty, but it's true that when we take these 4 nucleons over here, these 4 protons, and the 2 electrons, and we mush them all together like this,
It's
we
106.
get the helium out, then the helium will be less massive, and there's going to be excessive energy released. And we are past the date by like 1 minute. I wouldn't want to interrupt your access to your spaghetti miracoli or whatever you're going to eat.
So-
Actually, interesting
Can you
fact.
send a
when you say-
picture of the board?
I will
To
send a
the-
picture of the board, and I will also post this recording on YouTube. So I will do both.
Mr.
Blessman?
Blessman?
Yep.
If it like works for the other people in the class, would it be possible to have this meeting